Yeah, so for those of you who don't know me, I was a machine learning theorist. I'm still, but this work is quite empirical. For the last few years, I was a bit distracted, so I don't have other theoretical works I can talk about. So I thought this might be interesting for many people here as well. So that's why I chose this. And this is joint work with a former student at Stanford, and he's now at OpenAI. So that's why I changed the affiliation. So yeah, so I guess yeah, and also feel free to ask any questions because I think the talk is supposed to be for 30 minutes. I added a few slides to make it a bit longer, but actually we have a lot of time. So and also the language used here is probably for broader audience, so there's probably lack of detail. So feel free to ask any questions. Yeah, so I guess this is a very quick outline. So I guess number 3 and number 4 are what I added. So it used to be just about the paper, and I added a few slides about a quick survey of the area at October 2025. The date is very important here because the work was published online in January, and there were already like 20 papers in this area that you can read in the last 9 months, and there even like a V2, V3 version of one paper is, like or one line of work. So within 9 months. So it's kind of a lot of work. Anyway, okay. So let me get into the technical content. I think if you, I mean, Silicon Valley, if you ask around, especially in the startup ecosystem, I think reasoning capability seems to be appear to be a theme for 2025. Reasoning and agent, I think they are kind of like a little bit coupled to some degree. The rise of the agent is kind of enabled by this reasoning capabilities of the new models, especially with the long chain of thought trained by reinforcement learning. And here by reasoning, I think most people still mostly mean coding plus math. Of course, if you talk to some of the startups, I think they also mean reasonings in legal, finance, healthcare, so on and so forth. But I think coding and math seems to be the most important thing. So let's focus on that. And it's also easier there because, I'm going to talk about math, which is part of the theme here. So, and also for math and coding, in some sense, it's easier to study because it's very abstract. You don't have to think about grounding in the real world. You don't have to think about, if you do reasoning in finance, or legal, there are so many contexts that the model needs to understand about the real world, which is make it harder to study. At least it requires more data. So that's why math and coding is nice. Okay, we're going to talk about math, AI for math. I guess, when I talk about this, especially to relative mathematicians kind of audience, the first comment, that I often, the first question I often got is that, do you really believe that large language model can replace mathematicians and solve Riemann hypothesis of P versus NP? I think one of the common concern seems to be that large language model don't really understand and just do pattern matching. Here's my response to this. So my response to this is that, first of all, it depends on what's the baseline. If the baseline is the previous generation of automated theorem proving, like if you do the search-based automated theorem proving, for sure, I think at least I have a high confidence that those systems don't understand. If you just if what you are doing is just doing some kind of like a clever search, clearly they are not using mathematical intuitions. You are just doing deduction, search-based deduction. So those models don't understand. So no matter what you do, you are probably better than that. And then whether large language models can understand, that's very hard to argue, because this area about why large language model works, the theory is kind of like liking in some sense. But at least on an observational level, I can list a few things that I feel like large language models are very similar to human mathematicians, and are very different from the more classical search-based automated theorem proving. So both large language model and humans can extract vague intuitions from few short or many short examples. If you ask large language models to explain the intuitions, they will do something for you, right? As if, like, if you ask a mathematicians why you prove the theorem in this way, they'll tell you something. Sometimes you don't understand, sometimes you understand a little bit, right? So, and pattern matching, I think humans do that as well, right? At least, for me, I cannot speak for you, but like when I try to prove a new theorem, I try to first pattern match a little bit and see what are the related papers and I can read. And sometimes those related papers actually not that related; they looks similar. And I think hallucination is one of the issues that people talk about, about large language models. But in some sense, it's also just another way to say imagination, right? You have to imagine it a little bit and then verify whether that's right. In most cases, it's wrong. But sometimes, you hallucinate the right thing, or you get closer towards the true proof. Anyway, at least I probably hallucinate a lot when I try to prove theorems. I think it sounds like a large language model is pretty good at that. And I think recently, there's this long chain of thought. I guess just for people who are not exactly familiar with the area, so I think the innovation is that you can let the model to think for a long time, self-generating, autoregressively generate a lot of tokens, which are thinking tokens, and then you generate answers. So as opposed to you answer the question directly, or you generate a proof directly, you first generate like 5,000 tokens, which is like very kind of a crappy. If you look into the chain of thought, it's kind of not that kind of like a rational sometimes. And one of the very important things, I forgot to cite the papers, but I think there were probably 3 or 4 papers early this year, which are studying how why chain of thought helps. I think there's a few papers that link this to the humans cognitive kind of like behavior, which is self-reflection. I think there's actually one paper by Goodman at Stanford and his team, so which actually tries to figure out what the long chain of thought is doing, and there are a few cognitive behaviors by humans, and it turns out self-reflection is pretty much the most important thing, or maybe the only important thing according to the paper. So basically what happens is that if you look into the chain of thought, the large language models have a lot of cases that it says, oh, wait for a few, let me check this again, or wait, let me rethink again, maybe the answer above was wrong, and then you keep going with that. And another evidence about this is that people try to fine-tune or use reinforcement learning on top of Llama, on Qwen, Qwen and DeepSeek models, so on and so forth, to get the reasoning behaviors. Of course, you don't have access to the GPT model, so you cannot do that. So people tried all of those, and it turns out that for Llama, it doesn't work. For Llama 4, Llama 3, it's very hard to get the reasoning behaviors, but it's much easier to get the reasoning behaviors from Qwen. And even though Qwen is supposed to be a relatively weaker model in some cases, and one of the difference seems to be that if you use Qwen by itself, without any kind of like RL tuning, it already does some of the self-reflection a little bit. And you need some kind of like seed idea about how to do this, and then you can use reinforcement learning to amplify that behavior, and the behavior will help you to eventually solve more and more math problems. So yeah, I think that's so in some sense this is kind of like probably relatively a consensus that these large language models does have some capability of self-reflection within the context, not by training, but like you just if you keep running it, it still have self-reflection. And also another interesting, in my opinion, all of these are subjective opinions, of course, right? In my opinion, is that if you look at the limitations of large language models, actually they share the same limitations. At least I cannot do anymore, like a long mechanical deductions anymore. So and large language models still are not very good at doing numerical calculations. If you just ask it to count, you give it a list of numbers and you say, can you take the sum of this? I think like as of like a few months ago when I was making these slides, I think I tried a few cases. It still sometimes makes some mistakes, even just for a summation of like 20 numbers. So I think in some sense it sounds like the large language model are very good at thinking on an intuitive level, but not very good at thinking in a very precise way sometimes, which seems to make it similar to humans. And in some sense, I think one thing I didn't have here is that if you just extrapolate based on the last 10 years of history, it sounds like the models, it's really like imitating brains, right? So in some sense, what humans are good at are what the models are good at in some sense. There are all kind of these counterintuitive things. Like, for example, at the beginning, people say, oh, large language models are not going to be as good for creative tasks. But actually, that's the first thing that got solved by large language model. Like, you can have like all the art, music, all of this, right? And actually, like what large language model is not good at drawing or generating images is that when they are precise, kind of like some dependencies in the image is not very good. But if you just need a very artistic one, actually sometimes it's pretty good. Okay, anyway, and another argument here is that if you think about how fast we are moving in the area, it's pretty kind of impressive. I think, I don't know, like this is just illustrative. I didn't really just check carefully, but I think 1 year ago, maybe people, large language model as good as like people, mathematicians in 1500 AD, and this year we are probably as good as 1700. The question is like, human. Basically, I'm saying like humans are didn't know all of this, by themselves, from day one. This is like it takes time to develop. So why not? If humans can go from here to here, like it was like a 500 years, and if you extrapolate here, you'll probably believe that large language model can be better than humans at some point. Of course, this is like you cannot really take this on the face value because these models actually access the data from here. So that's one thing. But still, I think my main point is that humans didn't know all of this math from the beginning, right? So if humans can evolve and figure it out, why large language model cannot?
I was just going to be a contradictory.
Yeah, of course, yeah.
I was just going to say, but humans didn't, between 1500 and 2025, become smarter. We just gained more knowledge. And we learned that we need to improve their reasoning capacities. That's very different in terms of, to be a very different analogy, right? Like the humans, it was just creating the knowledge and not becoming better mathematicians.
Wait, let me think about this. Right.
Newton was as good as a mathematician as we are.
Humans didn't get smarter.
Yes. Humans didn't get smarter. I don't know. I feel like humans did get smarter, right? Because if Newton, is alive now, I'm not sure, right? So like he would have to learn all of this. Yeah, but but large language model is already as yeah. I don't know, but maybe. But large language models can get smarter as well, right? As you train them more and more, But maybe let's not. But I think when Newton is so. But how about not Newton? But like let's say let's say someone like 10,000 years ago, like a.
No.
No, it's okay. I love this. Like I'm thinking so. But do you think like the people in 10,000 years ago are as smart as we are?
It's been an evolution, but I think the evolution in brain capacity is at a longer scale, right? Like if Homo sapiens is like 11 species of Homo sapiens, and each one was smarter and smarter.
Intelligence is not a one-dimensional quantity, so there's full discussion.
Anyway, it's not an important part of the talk, so I'm gonna.
Yeah, it's kind of important for me, but but I think my argument would be like maybe if you don't use Newton as example, but if you use like someone way in the like 10,000 years ago, those people who only know how to kind of hunt and right, so like like I think the human intelligence actually improves pretty fast. In my opinion, right? Like since when people start to know how to use tools, I'm sure. Anyway, okay. Anyway, okay. So, but I think maybe another thing is that at least so far, like it didn't seems to there's no evidence for that like everything we have tried to imitate humans to do like in some sense we are on track of like kind of like being able to simulate human brain in some sense. So the artificial network seems to be very good at simulating human brains so far from what I see. Okay, anyway, so okay, now let's talk about some more objective stuff. Okay, so still on the high level. And why formal theorem proving? By formal theorem proving, I mean we're gonna use formal verifiers like Lean, Isabelle, or Coq. I think Lean becomes actually the default. So these are kind of like languages, where you can use with which you can use to write proofs, and then there's an automatic verifier to verify the proof because the language is defined in a way such that verification is automatic and objective. So and what are the kind of why formal proofs but not natural language proofs? I think there's no fundamental reason here. It's all pragmatic reason, especially for academia. So first of all, you abstract away some ambiguity of the natural language, which actually this is probably a double-edged sword because sometimes ambiguity is actually good for maybe building intuition, I don't know, for pattern matching. So I'm sure when two mathematicians are communicating with each other, some ambiguity is there, like which sometimes might be useful. But for us, like for when you really get the numbers, it's kind of like ambiguity is always kind of a bit challenging to deal with. You have objective and reliable evaluation. If you use natural language, you cannot evaluate on thousands of problems that you don't have solutions for. And you will see, like in all of the evaluations here, we're evaluating on thousands or sometimes even millions of problems, and none of them we have solutions for. We don't even know whether the statements are correct. We just say, oh, we proved that 20% of the theorems in this 1 million data set, 1 million theorems data set, but we don't know whether that 1 million theorems are all correct. And actually, if you sample and you can see 50% of them are wrong. But still you can have objective evaluation because if you prove it, it's proved. It's correct and proved, right? So, and no reward hacking, this depends a little bit more about details because, if you, one of the ways that you can deal with this is that you can design a reward model to evaluate whether your proof is correct or not in natural language. And this seems to be actually successful effort. There are contradictory kind of like sentiment about this way of using reward model because I think back in 2022, 2023, when people studied RLHF, like reinforcement learning from human feedback, there you have to build a reward model to simulate humans' reward. And there were a lot of like reports saying that if you train this reward model for simulating humans' reward, and the large language models that you are trained to optimize for those rewards will hack the reward eventually and find out some kind of gibberish that make the reward model feels that it's very high reward, but actually those are the cases that are OOD out of domain for those reward models. So you hack the reward function in a weird way. But here the reward function, as you're going to see, is going to be the verifier's results, which is super objective. There's no way you can hack it. The only thing you can hack it is sometimes you write a very lengthy proof that is not necessary, but still is correct proof. And because of number one, in some sense, it's possible to have small scale research. We are always amazed that 7 billion parameter models is enough to prove so many theorems, as you'll see. And you don't have to train with trillions of tokens because again, this is subjective. I do believe that the reason why you need such big models for GPT-5, so on and so forth, is because most of those parameters are storing some kind of knowledge of the real world. It's about what is the best restaurant in Cambridge, so on and so forth, right? And you don't have to use those parameters for those things anymore if you only focus on formal theorem proving. You just have to understand linear and proofs. And the main caveat is that the formal theorem provers is much weaker than the natural language provers. so it's very hard to publish a paper that's saying that, oh, this is the state of art among all possible models. You have to say state of art among all the 7B models, like trained for lean provers. But that's probably, anyway, you have to accept for academic research these days. Anyway, okay, so that's the and maybe another interesting fact is that the natural language the off-the-shelf models like Gemini, so on and so forth, they are not that good at lean. So if you use them on a lean problem and ask them to generate lean verifiable proofs, they are not as good as any of these models we're going to talk about. So basically, you can indeed get state of art among all possible models for lean theorem proving, interestingly. But that could be a different reason, just because like the Gemini was not trained enough on lean, so it doesn't really understand lean enough. I think that's actually the case. So basically, if you look into the details of the generated proofs by Gemini with lean language, most likely it gets the right idea, but it just didn't get the details right. Sometimes it used the wrong grammar, sometimes it misunderstood the lean verifier, so on and so forth.
I think some experienced if that was the case until about 3 or 4 months ago, and it is no longer the case. They're actually useful now in Copilot for writing lean.
Yeah. I think things are changing very fast. Yeah. So cool. Okay, great. So okay, so and just for those people who are not familiar with lean, I'm not that familiar either. So most of this is agnostic about exactly what the language is about. So these are the lean language. It's pretty much just a translation of natural language in my opinion, just to make everything kind of more precise, so that there's no ambiguity. And you can express, no matter how complex the proof is pretty much you can always express it. Yeah, nothing special here. Like as you can kind of guess. I don't really like that much about this kind of things. F z y x means f parenthesis z comma x. So you have this simplified ways to to write it, which is kind of interesting. Okay, anyway, so okay, so some of the I'm gonna have a longer list of like works after we published the paper in January 2025. So these are some of the works before that. So there are some evaluation benchmarks. There is something called mini F2F. Now I think this benchmark is pretty much dead because we got 100% accuracy on it. And these are kind of like high school context theorems in Leon's Isabel. And there's something called Proofnet, which is some college level theorems. I think this one is pretty small, like maybe thousands of questions. And there are PutnamBench, which are only 600 questions, which are translated from auto-translating to lean from natural language. I think these are college level kind of computation tasks. There are 600 questions more or less, and probably 200 of them are wrong because the translation was wrong. I think we call it auto-formalization. The auto-formalization was wrong, and the best number people got right now is kind of about 300 questions out of 600. And there are plenty of like papers, before this when I think the main thing is like the DeepSeek prover, which has actually 2 versions. I think this is the 24 is like the V1, and now they have a V2 version in 2025. And there are some kind of like tree search based methods which are like using kind of Monte Carlo tree search to search for the proofs. Yeah, and I think maybe the training data set is interesting. So this is actually another area where there are existing data sets which are relatively high quality. So first of all, to do any of this, you do need a library of like lemmas and definitions, because you cannot do everything from ground up, right? So like every kind of papers you write, like they're also maybe like if you list all the definitions of for your lemmas, from the axioms, it's gonna be like probably 10 pages, like you have to even define what the natural number is, right? So so those are all kind of like in some of this. I think MATLAB is the default one people are using. So these are libraries which were built for automated theorem proving for the previous generation type of like technology, and you can just take them as your libraries so that you can get a definition, so on and so forth. And there is I think AFP is a library with proofs. I think MATLAB is kind of have proofs and mostly definitions. And then people collect more kind of like data set, from auto formalization. Lean workbook is one of them, which is translating all of this into Lean. So these are all translated by large language models. So basically, this Lean workbook has probably a few hundred thousands problems, no solutions, because only the problems got translated, and half of them is kind of like mistakenly translated. So you shouldn't expect to get 100% accuracy here. You can only get probably 50 at most. Okay, so these are just some basic ideas. And now let's talk about some of the baseline approach. I think the baseline is kind of like RL, basically the vanilla RL, where you just use the large language models and reinforcement learning to train these models, with the Lean as the reward function. So basically, what you do is it's actually, RL in this context is very simple. Actually, in this what they call expert iteration, which is just the most vanilla version of the reinforce. What it means is just that you first generate proofs for the statement. You are given a lot of statements, and these statements don't have proofs, and then you just generate proof with your large language model, and then you use the Lean verifier to see which proofs are correct, and there's a binary reward. If it's correct, you keep the proofs, and if it's wrong, you drop the proofs, and then you get basically the next round of the training data, which are the correct ones. So basically, you have correct statement and proof pairs, and then you use this new this set of like correct statement proof pairs to train by just essentially supervised learning by training with the perplexity as the loss function.
So you mentioned that there's analogies between the language models and the humans, and so this kind of seems like one place where like this training paradigm seems quite different, right? Because when you're learning math, it's not like you write 1,000 proofs, you give it to the teacher, you get scores, and then you look at the correct ones and then you retrain yourself on those. I feel like that's quite right, no?
So what do you think a human do?
I mean, I think it's more modular somehow. Like I think I self, like at least I would self-verify on a lot of different things. Like, I have some derivation, and that part of derivation I can check myself that it's correct. I don't like, it's just wasteful to generate thousands of proofs, and then I mean, it's in a very inefficient way to learn. I don't
Yeah, I think wasteful is less of a concern because these machines will be trained on much more tokens than any of the human mathematician, right? And also, like these statements are not that hard so far. Like they are, what do you think? The statements here are probably your modular kind of lemmas in some sense. And you can also have a curriculum for that. You can start with simple questions and then train for longer, harder questions.
Comment, because there's certainly truth to what you say, but in making that comparison, keep in mind that all the machine learning systems have a sample complexity, which is at least 1,000 times worse than human learning. And so,
yeah, but that, if it's just only 1,000 times bigger, it's fine. The only question is whether it's kind of like exponential or kind of like n squared, versus n.
If a Lean program fails to compile, how much information does it give you about what went wrong?
Yeah, so far in this algorithm, you just assume it only tells you a binary thing. And I'll talk about some of the other works which use the feedback from the Lean prover. Yeah. So it basically you have a error trace if it's wrong. Okay, what are the issues with this? I think okay, I guess I do believe that there's not enough advanced theorem statements for us to run RL and generalize to other open questions. So I think they are probably not like college level questions. They might be enough graduate level questions, but it's kind of like a pyramid, right? Like the harder the questions are, the fewer the statements are, right? So, and I do believe that you can do this, and here the thing is that you want to generalize to other statements, not only just solving the existing ones. So that's kind of like so basically we don't have enough data. The more advanced you go, so in some sense, it sounds hard for me to believe that we can just keep doing this and go beyond the difficult level of the existing statements. And technically, I'm not sure whether I have the slides here. Yeah, so technically you also have this so-called sparse reward problem, which is not surprising. Basically, it's very difficult to find correct proofs, and this also slows down the training by a lot. So the more advanced you are, the harder it is to find the correct proofs. And basically, before you try 10 times, you get one proof and you reinforce that, and that's great. But then later on, like 95% of the compute is wasted on unsuccessful proving attempts for harder and harder stuff, and that makes it very hard. So so basically it's a very long tail. So basically like yeah, maybe I think I realized that this plot is not very useful, so maybe just ignore it. So basically what I'm saying is just that, I think like after a while, after you get the easy questions, then you just have like 1% of success rate to find proofs, or maybe sometimes even less than that. Let me see what I don't have a plot like that. So, and also people realize that the scaling curve for all of this is very bad. So basically if you draw this is the time and this is the accuracy, it's always like this. It's always kind of like gonna plateau. And if you draw, so this is accuracy and this is time. And if you draw on this side a log time, then it will look like this. So basically it's log in linear in most cases, and which is very bad, because sometimes it's even worse than log in linear, because log in linear cannot go, if you cannot believe that it's always log in linear, because it's going to go above 100% eventually.
So this is inference time or training time.
This is training time. Yeah, because here I don't have, there's no inference time. It's like we are measuring. Just, there is you can do it. Yeah, yes. I think for the inference time, if you draw it, is similar. It's just different kind of slope. And actually, if you look at the OpenAI's 01 blog post, they have this figure, and this is like this, and this is log time. But still, people are very excited about it. I think there's some other reasons for that, because in some sense, log in linear is not a big deal if you spend 10 million, 100 million, or maybe $1 billion, for OpenAI scale. But at some point, it's going to be a problem, because like you cannot keep going with this. Because at some point you say, oh, I already spent like $10 billion a year, and now I have to spend $100 million a year to get 5% more accuracy. The ROI becomes problematic. So yeah. Anyway, so basically, I think in some sense I don't see that this can be a bootstrapping kind of like loop that you can run forever. So ideally, you want to have a system that can just keep training, and you just throw compute at it, and maybe after 10 years, then it gets to the Riemann hypothesis. And so far, none of this can, in various dimensions, it doesn't work. It doesn't go beyond a difficult level, and also these curves are not great. So I think that's kind of the questions fundamentally want to address, even though of course this paper don't address all of that. Anyway, so then I was kind of thinking like, going back to this, right? So like a hypothesis is that neural networks are very good at simulating biological neural networks. But maybe there are things that we are not simulating very well yet. I'm sure there are many still. So what are the kind of like what did the human mathematicians do in their development of math that are not captured by neural networks? I think I'm using two words. One is the trial and error, and the other is in silo. So in some sense, first of all, the reinforcement is of trial and error, as Edgar mentioned. So and also this reinforcement is kind of like you're just trying yourself, right? So of course, it's not clear why the large language model have to simulate humans in all the dimensions. But if you believe that these are some of the human collaborations between humans are useful, then probably we should give it a try. That's kind of the argument here. So so basically, I'm trying to figure out what are the useful things human mathematicians did, and whether we can simulate those as well. So one of the things that we identify, among many other things we are trying right now, is that it sounds like human mathematicians does a lot of practices on variance and extensions of knowing theorems. As a graduate student, you probably take a textbook and do some exercises there, or maybe you discuss with other people on variance and of known theorems, and also they propose and prove conjectures. So in some sense, the training data set that humans are using are bigger than those kind of like theorems in the textbook, because they are exercises and conjectures. So that's pretty much what we are trying to do here. So basically, we want to have we want to have an algorithm which does the following. So there's not only just a prover, but also there's another model. Actually, it's the same model with different prompts. So another role, let's say, called conjecturer, and the conjecturer generates some statement. Generate some conjectures. And the way that we generate conjecture is that we give the conjecturer a statement X, which we know are correct, and we let it to generate an extension called conjecture Y. And conjecture Y could be more difficult than X, or could be just a variant of X. Sometimes, actually, in reality, sometimes it's maybe even easier than X. We can't really control, but we just generally call them all conjectures. And then the prover will do the trial and error reinforcement loop to try to prove the conjectures. That's pretty much the main idea. It's very simple. So in some sense, I think, but the conjecture is not given for free because we have to train them. So basically, it's kind of like they train each other in some sense. So the conjecturer will give a curriculum to the prover to some degree, right? It will generate more data for the prover to try. And the prover will also give feedbacks for training the conjecturer, because at the beginning you see, okay, actually we have seen this a lot. At the beginning, the conjecturer is just doing some kind of like random stuff and generating bad conjectures for various. Actually, throughout this is pretty much basically the whole research is about like every day you look at what the conjectures they are generating and see what's the problem and try to see there's some ad hoc fixes. So you see a lot of problems with the training the conjecturers, but generally the idea is that you want the provers to give some feedback for the conjecturers, right? For example, if the conjecturer is generating trivial conjectures, then that's known by the prover. The prover say, oh, this is too trivial, and the conjecturer will be incentivized to change. So that's pretty much the main idea. And maybe just give you a spoiler, like some of the examples. I think actually now as of today, we keep working on some of these ideas. So the questions become harder and harder. But as of January, I think these are the level of kind of difficulty for the problems. So sometimes you just you have a conjecture and you have a C theorem, and then you generate a conjecture which is pretty much just a variant where you plug in. Actually, this one is you just make it a little more complicated, and sometimes you simplify a little bit. Things like this. Yeah. So okay. So. And okay, so this is the diagram of the more concrete algorithms. So I guess I'm just gonna make it a little bit more formal than the previous slides before. So so basically, what we do is that we have this part and this part are new. So as I said, the conjecturing part is that giving a C statement and proof, and actually later we realized that probably you don't even need a proof to generate a conjecture. You just need a C statement, and then you generate a related conjecture. And then you try to prove them. So now you have more things to prove, and this part is the same, except that you're providing with more statements, both the original statements and the conjectures, and then verify the proofs, and then you select the ones that are correct, and use those to give feedbacks for the prover. That's the standard reinforcement learning. And then the main thing is really just how to give feedbacks for the conjecturer, right? We still use reinforcement learning to train the conjecturers. The question is, what's the feedback? What's the reward function for the conjecturer? And by the way, I think maybe some of these don't really make much sense for you. Like we don't use any additional feedback from the verifier, no tree search for this paper. Later people add more and more components. Yeah. Okay, so I think the hard part is that how do you design these conjecture data sets or the reward function for the conjectures. So and I think basically we want elegant, approachable, and challenging conjectures. And what does that mean? There's a few slides discussing this. There's an elegancy filter, which is very high talk, as you see. And for approachable and challenging, that's easy. So you just say, oh, I tried 32 times. I tried to prove the conjecture 32 times. And if at least one time the proof is correct, then you know, first of all, you know conjecture is correct. Because otherwise you don't even know conjecture is correct without a correct proof, right? And maybe just even doesn't even pass the syntax check. So at least you need to have one correct proof, but you cannot have too many correct proofs. If the number of correct proof is too many, then it means that it's not challenging enough.
Just to be clear, are your models conventional, like standard pre-trained large language models, or are they trained on control data sets, or what kind of models are you using?
Oh, you start with existing like a model. Like I think we start from DeepSeek Prover 1.5.
Conventional.
So yes, that's true. Technically speaking, I think the DeepSeek Prover 1.5 was a continual pre-trained version of the more generic DeepSeek models.
Okay, that was my question.
Yeah, and for the prover it's trivial. Okay, which is the same thing. Okay, so basically now let's discuss some of the details about training the conjectures. Some of these details probably don't really matter. It's more like I want to give you a sense about what's the challenges here, and because many of these things changes as you change the algorithms. We have many iterations after that with a different student, and we have found out some of these issues are less fundamental than the others. So the key is that you want some diversity and some relevancy of the generic conjectures. For example, one of the interesting things we observe is that sometimes they generate these kind of things where you turn a a number theory question into a inequality question, and so basically, if you see this conjecture, P is a prime, then P squared is larger than 4. So you are not using actually the property of the prime that much. Somehow you're just using that P is a prime, then P is larger than 2. So this is not that great, and it's not very relevant to this. And actually, this was a serious problem. At some point, our conjectures are all kind of like fundamentally algebraic linear fundamentally like algebraic questions, even though they're all written in other kind of languages. So you can have a topology question, like it looks like a topology question, but actually it's just about some equations. So that was one of the issue. So the conjectures may lose diversity after iterative training. So what we do? Okay, this slide becomes a bit outdated because we found some new ways to deal with this. But at least at that moment, what we do is that we use a C statement and a proof and the lemma of the C statement, these three things to generate a new statement. So basically, you already have a correct statement, and you have the proof, and you have a lemma that this proof invoke, from the library. So you say, oh, I probably have like a I don't know, I don't have an example, but so basically, you want to make sure that the generated conjecture uses not only a similar proof, but also probably the same lemma as the C statement, so that they becomes very similar. And also we try to preserve the diversity of conjectures so that you can cover different areas of math, not only just the number theory, but also inequalities, algebra, abstract algebra, so on and so forth. And I think we did some kind of like matching. Maybe I'll skip this part as well, which is okay. Maybe let me give you a rough idea, because but keep in mind that this is just to give you a sense on how ad hoc this is, but not saying that it's the right thing. So what we do is that we generate some kind of like conjectures, which are kind of like the blue ones, and the unproved statements are the right ones. So there are in the unproved statements, there are 3 number theory questions and 3 inequality questions. But when you generate, you lose some diversity. You only have 1 number theory questions and 4 linear algebra inequality questions. And then you do a matching to reweight them, so that you try to figure out this one is close to this 3 and this 3 close to this 3. So then you put a higher weight for this blue one, so that you say, oh, my reward for this blue one is not only 1 now, it's actually 3. So that you give a higher reward for the blue one, so that next round the conjectures will try to generate more things closer to the blue one. So that's one of the ways to kind of like maintain the diversity. So basically, you just hack the reward function so that you can have more balanced.
And how do you do the matching? How does that matching work?
The matching is we are using some embedding models to compute distance, and then you do some kind of like you run like this graph matching algorithm based on the distance. Yeah. So okay, we want to prove. Okay, so this part is another thing, right? I've already mentioned this a little bit. So you want to have a hard to prove conjectures, which is already dealt with, but how do you get to like a simpler or elegant conjectures? So one of the issue, I don't have an example here. One of the issue we found is that you can have a conjecture which has like a statement is like 3 pages, and the proof is on like 3 lines, saying that you just do like some numerical algebraic manipulations. Especially for lean, you can simplify any very, very long kind of like equalities into by just so it have something called auto-sim, which is a tactic that can simplify any trivial kind of like equality kind of like manipulations. So the proof is just 2 lines, but the statement is a very, very lengthy kind of like polynomial kind of something like that. So it's clearly not elegant, not very useful for anything. All right, it's probably not useful for even exercise because it's just manipulation. And then we use this so-called elegancy score as augmentation to the reward function. So basically, we say we want the length of the the shortest correct proof divided by the length of the conjecture. You don't really know the shortest correct proof, but in the reinforcement learning, you do have a discount factor that tries to make the proof as short as possible. So in some sense, even though I say shortest, I just mean the length of the correct proof, which I assume is the shortest, and divided by the length of the conjecture. So you want the conjecture to be short, but the proof shouldn't be too short. So something like that. You want the score to be as high as possible. In some sense, you want the length of the conjecture to be short. We remove the conjecture with the lowest 20% elegancy score. So actually, how do you use this score in the reward function is non-trivial. We try to multiply this with this reward. It doesn't seem to work. So eventually, we just remove the conjectures with the lowest score and training on the rest of the 80%. These details are probably, I think I'm just repeating the same thing. Basically, we have, I think this is just, we can skip this. Yeah, I think this answers the question where we initialize the model by fine-tuning on top of this DeepSeek prover v.5. Yeah. And this is the discount factors I'm talking about. Yeah, anyway, okay, sounds good. So, okay, some of the results. I'm pretty fast. Wait, it's already 15 minutes. Oh, okay. Oh, sorry. Okay, I got the wrong. Okay, good. Okay, cool. Okay, so the results, right? So expert iteration just means RL, and parallel sampling means you just don't do any training. You just keep trying the base model. So parallel sampling just means like you try the base model multiple times, and you take you take the best of inaccuracy. And you can see that the scaling is much better. Still, it's kind of like slowing down. But on the x-axis, this is not log yet. I think if you take the log, I don't have it on the paper, but if you take the log, all of these are linear, but this is much better slope. And we have done ablations as well. For example, what if you don't start at the checkpoint at the beginning? You can start at any checkpoint and run the baseline, and you see that the baseline is slower than our algorithm. So basically, we have an advantage at any stage that we have tested on. So and these are okay. And when you evaluate, I guess there were some questions about this. Like when you evaluate, you can have like a path at k, right? K could be 1, could be 10, could be like 100. So basically, this means pass at k means you try k times and you see how many of those proofs passed. And this is the evaluation results where you can try changing the number, the k, and you can see that we're consistent better than the baselines. Sometimes this kind of things is counterintuitive. You can have that a model that is very good at pass at 1, but not that very good at pass at k. So that's what we are verifying here. And at that point in January 2025, we are the best. We have 8 Putnam problems solved, and the others can solve only 7. And also, this is not an entirely fair comparison because it depends on what data you use. I think this paper actually used a lot of data generated by Gemini or something like that. Anyway, so we are the best on every data set at that point, and there are some numerical numbers here. So it sounds pretty strong signal that this is working. There are some. These are some of the examples we can prove. Just these are some of the conjectures. I guess you have seen some of this. Okay. And typical conjectures requires longer proof for some reason which we don't necessarily understand, even though the conjectures are not necessarily always harder. We thought this is a good thing because if it requires longer proof, it means it might be harder. But eyeballing doesn't seem to tell that the conjectures are much harder. But in terms of the length of the proof, the conjectures are harder. So it's possible that these are just harder for the provers, but not harder for humans, which is still the right behavior. And these are some of the proved statements in the Lean workbook. I guess as mathematicians, maybe you want to stare at it for a second, to see how difficult it is in January 2025. So we can prove these kind of theorems. And in October 2025, I think it's half of the Putnam problems. So this is certainly not as hard as Putnam problems. Okay, we can skip this. So I only have 5 minutes, right? 2 minutes.
Last questions, maybe? Or do you want to?
Maybe let me just quickly go through the rest of 2 or 3 slides. I was thinking to spend 10 minutes on this, but I can be faster. So I think so basically this paper was published in January. Published means putting archive in January. And then after that, I think there's a large body of broader work on this. So I'm trying to group them in categories. So they are hierarchical proof strategies. I think this is what Edgar was alluding to as well. So the general idea is that you're given the theorems, the large language model first generates a sequence of steps or lemmas on a kind of higher level. And these lemmas can also be written in Lean as well if you want. And then you generate proofs for each of the lemmas. And then you prove the theorems using the lemmas. And you could also include many optional steps like taking the feedback from the verification, so on and so forth. So you can even retrieve some lemmas, so on and so forth. And how do you do this? I think one line of approach is use large language models for decomposition. You can use I guess I really mean that you prompt off the shelf like a large language models like Gemini Prover, Gemini Pro 2.5, so on and so forth, or Kimi like 2, and then you probably use some other models to prove the lemmas, or you just use the same model to prove the lemmas. And I can use also train the models to decompose better, and to train the model to decompose better, in some sense, you just try to make sure the models generate in this kind of format, and then you reinforce. And I think we still haven't figured out how to do the credit assignments. So basically right now, all of these papers pretty much when you are, so basically you just want the models to generate all of this, in this form. And then if the whole trajectory is correct, then you say everything is correct. Everything is rewarded, and otherwise you just drop the trajectory. But ideally, you probably should say, oh, if I generate one correct lemma, but all the other lemmas are wrong, then I should reward the generation of that lemma. And the hard thing is that how do you know a single lemma is the right lemma for the theorem if you haven't proved the theorem as a whole? Right? How do you justify this is actually the right lemma? And then there's a approach to use the feedback from the Lean compilers. This is just you give the feedback from Lean compilers back to the model, and you automatically always get some improvement. In some sense, it's an orthogonal approach. And there's this line of paper by called Godel Prover. They have 2 versions. The first version they trained, they formalized 1 million natural language problems into formal problems, and then you run expert iteration on it. So, but this is a much bigger data set than the Lean workbook that we were talking about, which is hundreds of thousands of questions. This is like 1 million questions, and you can get much better results. And then later, this is a Princeton group by Jin Chi, led by Jin Chi and Sanjeev. Then they proved they have a prover with long COT, and you can incorporate Lean verifier feedback. You can generate synthetic data similar to the STP work we talked about, but they generate synthetic data using Gemini 2.5. And then you can get even much better results. And then the most recent one that is really the best is this seed prover by ByteDance. So they actually have two papers, one called Delta Prover and later called Seed Prover, and they train 30 billion parameter models that does this hierarchical proofs that I mentioned in the previous slide, and then they can solve half of the Putnam problems. But actually, if you think about, because they are these mistakes in the auto formalization, actually they solve probably 75% of the correct ones. Okay, so I guess just very, very quickly, actually these are not very good open questions either. So I just open thoughts. So I think the main thing is just how do you train the conjectures with principles? So far it's very ad hoc. And basically it's just how do you make this, have some principles on how to do this, like how to iterate between conjecture and proving, how often do you conjecture, how advanced they should be. None of this is theoretically studied. We just kind of like a trial and error. And also maybe there are other aspects of mathematicians' work that we don't incorporate in a training algorithm, and it's useful to formalize those in some sense. Okay, I guess I'll stop here. Yeah.